Welcome back to ECE 442-542. This is a video that hopefully will allow you to prepare for the second attempt on quiz number 4 in ECE 442-542. I've tried to now lay out in this page the questions that were the least successful or had the lowest scores on them during the first attempt of quiz 4. And I'm going to probably give you a little bit more information so that you feel more comfortable with these concepts as you move out past this class. The first question is dealing with the pole zero mapping, discrete equivalent technique, and it's interested in matching the gains. And here what you need to think about, and now I've given myself a little bit more room, is we have in general, we have analog and then we have digital. We have the frequency variable S in the analog setting, and we have the frequency variable Z. Those are both complex numbers. When we're talking about frequency response, which is really what we're interested in when we're dealing with matching gains, here we're really we're evaluating S at j omega, and a lot of times we just let omega be 0, so S is equal to 0, or omega go off to infinity, and then S is going off to infinity. But over here in the digital domain, we then, that's a lousy E, but we now have this relationship between S and Z, and we can now say that Z is, if we want to know what the transfer function is going to evaluate to in terms of its frequency response, we evaluate that d of z at e to the j omega t. Suppose that somebody said, you know what, I have an integral controller, and that's now this k over s. So this is now an integral control. And they want to create a discrete implementation of that. And so now over here you would say, oh, I now can say that's some gain, my pole zero excess in S. So there's two different domains of pole zero excess. They could be in the S domain or they could be in the Z domain, and you'll need to be paying attention to that. But here our default is to, if we have a pole zero excess, then we will start mapping factors in d of z of the expression z plus 1. We'll put so many of those, in this case an integer L, in the numerator consistent with or related to the pole zero excess in the S domain. Here, if we map that pole at the origin, then that's going to map to z equal 1 over here. And if we said that our zeros at infinity, in the S plane are I sub z, then our default in this class is to say, oh, let L equal I sub z. But we may, if we now want to, preserve a pole zero excess in the Z domain, and now I'm not sure what I want to call that, but let's say that we now say I want 1, or I want a pole zero excess of 1 in d of z. Now to make that happen, in this particular case, we would actually want to lower that L from I sub z, which in this case, I sub z is equal to 1. we have 1, 0 at infinity in the S-plane. Over here, if we did the default, we would just say, oh, we want this one factor, z plus 1, to be present in the numerator of our discrete equivalent. But now, if this statement is enforced, we want a pole zero excess of 1 in d of z, then we would actually not want that L to be equal to 1. We would want it to be equal to 0. And in that sense, that z plus 1 factor shrinks down to just being a constant 1. So that then, if somebody says, oh, I want the pole zero excess of d of z to be some value, then you have to adjust what this L is equal to, that is determining how many of these z plus 1 factors you have in your discrete equivalent. Suppose now somebody says, well, let's match the gain in this integral controller. Hopefully you see that at s equal to 0, what happens to the magnitude of d of s? That now goes to infinity. And what happens over here? When z is equal to 1, which is the equivalent location in the z-plane to s equals 0 in the s-plane, z equal 1 in the z-plane, this also says, oh, wait a minute, that's going to provide a 0 in the denominator because we're evaluating this factor z minus 1 at 1, so that's going to go to infinity. So we can't match gains at s equal to 0. And you're going to find that for different structures of S-domain transfer functions, in this case an integral control, you can't match at DC because the gain is infinite there. So where do you match? Well, here you might just pick a convenient value of frequency omega. And depending on your system, in this case, it's k over s, so let's just let omega equal to 1. That says then that we have s is equal to j1, and we now have, for a magnitude of d of j omega, we have k over j1. The magnitude of j is 1, so now we have k, and somebody might have said, oh, your k in this particular design was 10. You can now use that information over here in the z-plane. Now you're looking at saying, oh, z is equal to e to the s, and s is j1 times t. You'll have to be given, or you'll have to determine a t, but you now have that. Now you would say, oh, let me find the magnitude of e to the jt in this d of z structure. And depending on what it is, let's just say we're enforcing a pole zero excess of 1 over here, then we would have a k-bar over e to the jt minus 1. And now you would set these two equal to each other. You have 10 is equal to k-bar over some complex number's magnitude. You can solve for k-bar, and now you have what you need. I've run out of space for what I wanted to continue doing. Let me go ahead and try to continue talking a little bit more about this notion of matching gains. This is maybe more than you wanted, but this was a pretty low scoring quiz question, so let me just keep providing you with a little bit more information. Suppose now somebody said, oh, I have a phase lead controller in D of S, and I want you to convert that into a digital controller. Well, a phase lead controller, let's just pick one, and we'll maybe talk a little bit more about this later in the class, but let's now say that we have that for our phase lead controller. If you're remembering your Bode plots, now at DC, this has some gain, and in particular it has a gain of 1, but then we'll find, then it will break and go up because we have a 0 at 1, and then it will flatten out. So this is now what the magnitude response of d of j omega looks like. In this case, we could actually match the gains pretty much anywhere we wanted. Over here, we would have a d of z that's going to be some gain k bar. Then we have a a 0 at 1. So this is now e to the st. This is e to the minus 1 times t over z minus e to the minus 10t. And our pole 0 excess here is 0. We have I sub z is equal to 0. So here we don't need to have that factor called out. So we don't have to worry about including this additional factor z plus 1 in the numerator of d of z. But I hope you can now see that, oh, I could actually pick s equal to 0, which is now down here, and that would be okay. That's not going off to infinity, and it's not going to 0. So you could pick 0. And if you did pick 0, then over here you would just let z equal to 1 in your matching. So now you would have d of 0, and over here you would have d of 1, and you would match those. Or you could say, you know what, I like this behavior in my d of s, so let me now let s go off to infinity and match the gains there. Then you would be looking at limit as s goes to infinity of the magnitude of d of s, and you can see that that's now going to be 10. Here, this was equal to 1. Now this is equal to 10. And you would then look at two different possibilities over here, but let's just assume that we're going to be consistent with what we've been doing and find then d of minus 1 over here in terms of our unknown parameter k bar and solve for that. We could have also just as easily matched the gain anywhere in there. It's bounded, so we could match it. So here I'm essentially saying we're matching here, or we're matching here, or we are matching in the green, and in this case I'm going to be picking with red, but you could now pick s equal to, let's say, j5, or it could really be any value. Let's just say pick a frequency x, and then over here you would then be looking at z is equal to e to the j xt, and using that in your d of z expression. And equating, this would now be the magnitude of, and that will be some number. You would then equate those, and that's how you would continue. Now one more of these d of s's, just to let you see that we have other possible behaviors or invalid places to try to match gains. Suppose somebody says, oh, now I have a derivative controller. So that now maybe your d of s is ks, but we know in practice we need to roll that off at high frequencies. Let's put a pole in there at 10. This is just a hypothetical, but now what does this look like in terms of its magnitude? If you remember your Bode plots, this is now coming up from the basement because of that 0 at the origin, and then it flattens off at 10. That means that you can't match, if you looked at d of s, when s is equal to 0, what's going to happen? That's going to be 0. And if you looked at what happens in the digital setting, you have some k-bar, you have a 0 at z equal to 1, so you have that factor, you have this factor. The pole 0 excess in the S-plane is 0, so we don't have to worry about that z plus 1 factor. And over here, if we evaluated this at dc, that would be at z equal to 1, and d of z with z equal to 1 is going to be 0, and that doesn't make any sense. Now we would be looking at 0 is equal to k bar 0. You can't make a call. So now you might actually want to, in this case, match gains there. And the easy place is to go ahead and match it out there at infinity. Or in this case, you would say, okay, let me match at s going off to infinity. Then you would be looking at the limit as s goes to infinity of this d of s. And for this particular choice, I hope you see that you now have that equal to k. And over here, you would then be looking either at z equal to minus 1, or you could, in fact, let z go to infinity and match either of those cases. That would be valid. Here, in this on the left, you would be looking at d of minus 1. And in this case, if you let z go to infinity, you see that you end up with k bar. So now you would be equating k with either the magnitude of d of minus 1 or the magnitude of or k bar, depending on where you matched. And that's really up for your decision making. So all of that background to help us maybe talk about matching the gains here. And I was hoping this maybe wasn't worded real well, but these are values of s. If you actually looked at these options, hopefully you would see that d of s, when s is equal to minus 1/2, d is equal to 0. Can't match. What about an infinity? When s goes off to infinity, d goes to 0, and you can't match. What about when s goes to 0? Now d goes to infinity, and you can't match. By default, then, the only possibility is to look at matching the gains when d of s is equal to j, or j1. And so now we would be looking at 2 times j1 plus 1 over j1 times j1 plus 8. You didn't have to go all the way through this. And then you would match that with your value of d of z, which in this case would be some k bar over two different factors. And hopefully that now helps explain how you could approach that problem, and I'm hopeful that we will do better on a problem like that on the second attempt. The second question was, suppose the following system will be controlled with a closed-loop bandwidth of 10 Hertz. What might be a reasonable sample period t? And you might have, and let the sample period have units of seconds. Here, what you need to realize is you're wanting to pick a closed-loop bandwidth, so in reality, this set of information is a red herring. It's not really needed to solve this problem. You're being asked to find a closed-loop bandwidth of 10 Hertz, and that's now an f sub c of 10 Hertz. And we're used to thinking in terms of omegas. Omega c is now 2 pi fc, and this may have tripped some people up, and I just wanted you to realize that units are important. This is now 2 pi times 10, and in fact the sampling frequency that we're using in this class is 30 times the highest frequency, and this is now the highest frequency, omega c, so this is now what we would be setting equal to 2 pi over t, which is our omega sub s, and you can now solve that for capital T to find a sample period that you want that's reasonable. Now we're back to this pole zero mapping. The transfer function is the same. Now we're playing on this, what's our pole zero excess? And remember, we have a pole zero excess in S-plane and Z-plane. We've been usually focusing on this I sub z, but in this problem I'm basically saying one wants to achieve a pole zero excess in d of z of 1. Well, if we did the default for this class, this would now be some k bar over z minus e to the, and there's a 0 here at the value of s that causes that to vanish, and that's now minus 1/2. You didn't even have to do all of this, but now you have minus 1/2 t over, you have a pole at the origin in the S-plane, that maps to a pole at 1 in the Z-plane, and then you have this additional pole, and the default would be, oh, my I sub z in the S-plane is actually 1. I have 1, 0 at infinity, or I have a pole zero excess in the S-plane of 1. So that would have said, oh, I need this L to be 1. That would be the default, but I'm asking you actually to do something that's non-default condition. Now we are saying I want the pole zero excess in d of z to be 1. That means that this L needs to be 0 so that this goes to 1, and now I have two poles minus the number of zeros is my pole zero excess in Z-plane. Here I have now 2 minus 1, and that's now 1 if I let L equal to 0. So in this case, it's asking you how many of these z plus 1 factors are required in the numerator of d of z. hopefully now you see that you want no factors of z plus 1 in that transfer function. Now I flip the tables a little bit on this question. I'm asking you, what is the numerator of d of z if you're doing a pole zero mapping discrete equivalent and they don't say anything about the pole zero excess in d of z. So now we are working in the default scenario, which says that we want L in our mapping to equal I sub z. How many zeros at infinity do we have in the S-plane? We have 1 now. And so now our numerator in our d of z is going to be some k bar, or k. It's going to have a z plus 1 raised to the L, and in this case, in the S-plane, I sub z was 1, so we're going to have that equal to 1 because nothing was said about the pole zero excess of d of z. And then we also need to realize that we also have that 0 factor due to this 0 in d of s. Or now we have, and you can now plug in the appropriate sample period t to get the numerical value of this e to the minus 1/2 t, and hopefully you can now see what the structure needs to be in your numerator for that answer. The next question on our list of quiz questions is determine the exact system matrix phi in terms of the sample period t associated with a zero order hold equivalent of the system. Now we're doing a zero order hold, and in fact we're looking at finding this, e to the at, where this e to the at is in fact determined, or a comes from that set of dynamics. We now can see that a is minus 2, 10, minus 3, 0. Whoops. This is now a minus 3x sub 2, so that now goes in the 2, 2 entry. Now you would need to find this phi matrix, and that requires that you take this Si minus A inverse and then inverse Laplace transform each of those 4 entries. This is a diagonal matrix, so the inverse of that symbolic matrix isn't quite as involved. Here you would have Si minus A inverse is now S plus 2 minus 10, 0, S plus 3, and you want to invert that. That's now 1 over the determinant, and the product of the off diagonals is 0, so we just have those two, and then you interchange the diagonal terms for a 2 by 2. You change the sign of the off diagonal, and now you have your Si minus A inverse matrix. You now have 1 over S plus 2. You have 10 over S plus 2, S plus 3, and here you have 1 over S plus 3. These two terms should be immediately inverse Laplace transformable. So you now have e to the minus 2t, e to the minus 3t. You have nothing there. And what does this do? Well, now if you partial fraction expanded that, maybe I should say an A1 and a B1. Now you would have some linear combination of e to the minus 2t and e to the minus 3t in the 1, 2 entry of that matrix. And hopefully you can see that your answer is depicted in one of those that's given in that structure. The next one is given a system, find the system matrix phi and a discrete equivalent using the backward numerical integration technique. And now we're doing state space, so you might want to go into your tables and you say, oh, here is my information. If I'm doing numerical integration, discrete equivalence, scenario number 1, and I'm starting with a state space representation, which means that I'm now working with this, I simply identify which strategy I'm looking at, and now my phi matrix I can compute as I minus AT inverse. So now up here I say, oh, that's I minus AT quantity inverse. And what's A? Well, A in this case is now minus 2, 3, 1, minus 4. And what I was wanting you to be able to do is invert a 2 by 2 matrix. I now have 1 minus a minus 2, and this A is scaled by t, so this now is going to be a t. Then I have a minus 3t. I have a minus t, and I have a 1 minus a minus 4t. And I invert that. And that hopefully will get you, you are given a sample period capital T. That should now allow you to find the answer for that type of a question. Here, suppose a filter with input R and output Y is modeled by the following system. And you now want to convert this analog filter. This is an analog system in state space. And you want to now figure out how do I discretize that, and you're asked for a sample period T. Again, you're dealing with this A matrix of minus 2, 3, 1, minus 4, and you're not told to speed the system up. You just need to keep the same dynamics that you started with. So in this case, we're looking at, oh, can I find, and maybe I'll switch, just because a lot of times when you're dealing with eigenvalues, they like to use lambda as a variable. You're really just looking at the eigenvalues of this A matrix. Those determine the modes of this analog system. You now have lambda plus 2, minus 3, minus 1, and a lambda plus 4. And you could now find the determinant of that. Or you now can hopefully see that you have lambda squared plus 6 lambda plus 5. That, in fact, factors. You want, if you're now digitizing this or discretizing this, you want to use the fastest omega. Omega 1 is omega 1 is 1 and omega 2 is 5. Because here you have lambda equal minus 1 and lambda equal minus 5 as your values. Those have frequencies of 1 and 5. You now use the fastest of those two. Those are now pole locations in the S-plane. You have a pole at minus 1 and you have a pole at minus 5. You want to now sample based on the fastest pole. So that now omega sub s is 30 omega sub fast. And again, that's equal to 2 pi over capital T, and you can solve that for capital T. Now we want a zero-order hold equivalent of the following system. Here is our system. It's a first-order system, and assume you want a transfer function model. So now that should immediately say, oh, I need this g of z. That's 1 minus z to the, 1 minus z inverse, z transform of g of s over s. Or we now can say, oh, I now have to find the z transform of this expression. And that you should be able to now partial fraction expand find the appropriate, once you've found A1 and B, I don't know why I did B2, but that's okay. A1 and B2, you can now find those in the transform table and then find the z transform expression, which in this case is what? A1 over 1 minus z to the minus 1, and this is b sub 2, 1 minus e to the minus 2t z to the minus 1, something like that. That's what's in here. And if you now distribute that factor 1 minus e to the minus 1 through, you should be able to clean it up and do the algebra to find the g of z, the zero-order hold equivalent of this original transfer function g of s. Here, during the process of using the backward numerical integration technique, and so now you want to focus on which numerical integration technique, find a discrete equivalent for the following and find the location of the zero. I'm not asking you to do the entire discrete equivalent. I'm just wanting you to find the zero using the backward strategy. And that now says that, oh, I can again go to my tables, but now I'm looking at the transform or transfer function representations. That particular question said backward, so now I simply replace everywhere I see an s, I replace it with z minus 1 over tz. So here I would have 16 z minus 1 over tz plus 1 over z minus 1 over tz plus 8 as my d of z. That can be cleaned up a little bit by multiplying by 1, and now I have in the numerator 16 z minus 1 plus tz in the denominator, which I'm not that worried about because of the question that's being asked. It's being asked for the zero. Now I can focus on that, and I now know that I have z minus 1 plus tz is equal to 0. I was given a t, so that now I can say, oh, I have 1 plus t, z minus 1 is equal to 0, or z is equal to 1 over 1 plus t. And you should be able to find your answer then for the 0 location in that question. And finally, this one now I've switched up a little bit. I said forward, and I've also said pole. The transfer function, was it the same? It was the same, but now I'm using a different numerical integration strategy. So you want to make sure, and I'm asking for the pole. So you can't just use the results that you had in the previous problem. you now need to go back and say, oh, now I need to replace s with z minus 1 over t. Now I have 16 z minus 1 over t plus 1 over z minus 1 over t plus 8. Here my number 1 can just be t over t, and I have 16 z minus 1 plus t over z minus 1 plus 8t, and I can now find what was asked for, which I think was a pole in this case. And now I'm looking at z minus 1 plus 8t equaling 0 to determine my pole location. So now z is equal to 1 minus 8t, and I think I'm given a t. I should now be able to find the appropriate 0. I think that should get you more comfortable with your second attempt on quiz number 4. I hope that helps. Good luck, and we'll be back.